where we left off is we were implementing merge sort together, and we kind of did a speed run through it at the very end, but I think the big picture is just the complexity of algorithms, how that can very much influence the resulting performance, and consequently why algorithms are an important thing to study and to explore. The analysis of why this is n log n versus order n squared for bubble sort, we came up with kind of a hand-wavy answer to that, which I think is sufficient for our current learning outcomes of this course. This one, merge sort, is logarithmic in nature because we're doing this kind of recursive dividing in half of the problem space. And log base 2 means every time we do it, we're split. There's that many splits we have to make to get from the original problem, in this case of size n equals 8, all the way down to the leaf node of the recursive call, or the base case of the recursive function, where we're doing a sort of size 1. What makes merge sort, I think, a little tricky in terms of implementing is not necessarily this partitioning part. This recursive call is something we've already kind of seen and have done in other contexts, but then to actually do the merge sort, there's this merging component as well, which is we're taking those values once we get to the base case. That function merge sort finally returns. We then start to merge these individual subarrays, and the idea in terms of performance there is that is then a linear operation. Again, hand-wavy is probably as far as we're going to get with that, but the idea being that sorting two arrays of size 2, where each of the individual subarrays are sorted, is faster than sorting an array of size 4 of arbitrary order. So we don't have to do a bubble sort on those subarrays or some other quadratic sort. We're just merging them together. And because they're relatively sorted, the left-hand side and the right-hand side is sorted, and maybe it's easier to see with this larger example there, the actual merger can be done via one pass through the whole array. Because either this value is less than this value, or it's not, and we're just doing this pairwise comparison, and you just have to do it once because the whole thing is actually sorted. In terms of the code for that, well, we spent a little bit of time kind of building a little bit of a framework for generating data, as well as calculating the runtime fairly precisely associated with the execution of both our n squared bubble sort and our n log n merge sort. But the main merge sort piece was doing exactly that. So to make our code a little bit easier to read, we created subarrays for the left-hand side and right-hand side called left and right, copied our big array data of the right range into that, and then our actual merger is just looking element by element and doing individual comparisons of L of I versus R of J. If it's less, let's grab the L element, otherwise let's grab the R element. Eventually we'll finish one of the subarrays before the other subarray, so we just have a little loop that once the first subarray is finished, the rest of the elements must be coming from the other subarray. And that's all we had, and that is the crux of merge sort. One other thing I added after class is I did want to show the scalability and performance of this, and we did a little bit of it. We had implemented as a quick programming hack, the variable length array, where we have a variable defined in our function. We then have a stack array of a particular size that's variable in length. And I've told you in the past that that's not guaranteed to work. There's limits of how big that can be, and that is still true. So one quick refactor of the code would be just to do dynamic memory allocation for that part. These two lines of code, or the dynamic versus static allocation, are equivalent in terms of what the rest of the code has to do, but it has implications for where our stuff is put in memory and may have some performance implications. The other gotcha for this, although maybe this should always be our common practice, if we are doing dynamic memory allocation, each time we call this merge, and we're going to call this merge lots and lots of times, n log n, or log n times we're going to call it here, then unlike some of our other use cases of dynamic memory allocation where we allocate something and then the program exits, we don't care about it, in this case we do definitely want to free that memory that we've allocated every time we've called that merge here. So just to kind of go back to where we were, it may not be that obvious when we have an array length of 100. Both our merge sort and our bubble sort are quite fast, because of course there's some overhead in doing the merge sort. There's all these extra function calls. Now there's all this extra dynamic memory allocation. It's not surprising that for certain n values, our n squared is faster than our n log n. That big O, that complexity analysis, just tells us the general trend of the performance It's not a strict equation. We can just plug in a number of n and get a result back out. There could be different constant offsets here. The setup time for the program could be quite large potentially, but we should start to see the benefit of our n log n versus n squared as we start to get to larger runtime. So here's bubble sort with 1 million elements, and 1 million is not a ton, right? 1 million is a lot of integers, but that's nothing in the data sizes we have to deal with on a day-to-day basis. And we can see it's quite slow. And there we can see, well, what happens? You now have 1 million cross 1 million type of complexity. That's a lot of things going on here. It may in fact take too long for us to even run to even confirm the results are correct for bubble sort. That's 10 to the 12th power. That's a lot of runtime. Whereas if we do 1 million with our merge sort, so blazingly faster. Even though at first glance the code's really similar, so complexity matters. The structure of our loops matter. Now in this case we can go even bigger, and I think we'll be okay. That's 10 million elements, and it will be slower. It's still going to grow in terms of n log n, but it's still a pretty manageable amount of milliseconds. I don't really know what our upper limit's going to be. That's now sorting 100 million integers, and that's a decent amount of data. That's 400 megabytes of data that we're randomly generating and we're sorting here. And based on this, it's going to take another factor of a little bit more than, it's going to grow and be slower, but it's still going to be a manageable amount of runtime. So I think that's the important takeaway. Not, do you know how to code merge sort on the spot? That takes time. And frankly, when you have to do it, you should look at a reference and you should look at other examples and try to compare and try to apply it to your circumstance. But understanding that there is a difference. By taking the recursive solution that subdivides the problem, we do get better performance. And I think it's fair to say now, significantly better performance than the kind of what we would call the naive kind of iterative approach that we were learning when we were just trying to understand for loops and later arrays and later functions, which is just taking something that makes logical sense to us and not thinking about the complexity of it. For a classroom environment, we don't usually care as much about scalability. We just want to get things to work, and we get our grades in and get our successful passing of our program required outputs. But in the real world, that does matter quite a bit. And that's why it is important, I think, to study algorithms. The challenge is that there's many, many different kinds of algorithms. So I have some content here about another very well-known, very popular n-log algorithm referred to as quicksort. Quicksort has some things in common with merge sort, whereas merge sort just says, hey, cut the thing in half and subdivide the problem. Quicksort instead attempts to pivot the data into 2 buckets at a time. Given a pivot element, which can be either randomly selected or selected based on some heuristic known about the data, take half the data, put it in the left-hand side, half the data, put it in the right-hand side, and then recursively do that. So it is different than merge sort, but it's not that different. Again, merge sort, cut it down the middle each time. Quicksort, cut it based on a pivot element that you then decide on based on some heuristic. It tends to then have potentially better performance than merge sort, depending on what knowledge you already have about the data. It can also have very bad worst case performance, which was what makes it an interesting algorithm to study, because if you pick this pivot element very poorly, perhaps all the data is in fact larger than that pivot element and you haven't really sorted anything at all, and you basically have implemented a very inefficient bubble sort if you choose your pivot elements poorly. But that's kind of the problem with algorithms. That's why it's this whole other course or sequence of courses. We could spend time and try to implement this using the pseudocode type of approach. I think it's close enough to merge sort that it's probably not the best use of our time. And then it goes back to my initial point about algorithms. You're going to go for your first internship or co-op or full-time job interview. And depending on the nature of the job, if it has any aspect of coding, well, interviewers don't really know what to ask either. So they'll ask you, hey, can you implement quicksort for me on the dry erase board? That is not an atypical interview programming question. They don't necessarily care, can you get the syntax exactly right? What does the interviewer want? Well, first off, they want to know, is this person completely clueless? And you want to get past that hurdle. Like, oh, I have no idea what you're talking about. That's not a good answer. But they don't necessarily care that can you do this exactly right, because that's not how we normally program, right? We don't have to write on a piece of paper or a dry erase board a perfectly working piece of code. We have an editor open. We do some research beforehand. We read documentation. We try things and we kind of debug the problems that occur. And we don't do it in 5 minutes. We take our time and try to do it properly. But being aware that there's an important reason to have a function or an algorithm like quicksort can help you get partial credit towards the correct answer on that question on an interview. I think a better answer or a potential answer that even if you never take another programming or algorithms course that you can use is, well, I know that if I want to sort data, just like when I know I want to copy data, it's unlikely that that me as a junior programmer am going to be able to do better than kind of standard library approaches that have been looked at by thousands of people over decades now to solve that same problem. So one other takeaway I want you to have, and we'll spend some time playing around with it, would be, okay, not to be snotty during your job interviews. Sometimes it works. I can't recommend that. But to say, hey, to recognize and maybe even have the humility to recognize, okay, I can kind of struggle my way through a halfway kind of working, sort of efficient quicksort implementation, or I could recognize that standard C library, and not just C, every well-used programming language and framework you will ever utilize is going to have some built-in sorting function for you to be able to use. And I think that's probably the right programming interview question. Okay, here's my half-hearted attempt to implement quicksort, but by the way, I would never do this. If I needed to sort something in my program as part of this job, I would use a standard library implementation of it because it's going to do a better job. We will measure performance here. I'm kind of curious what we'll get back out because I haven't actually tested that yet. But all programming languages, and C is no different, has a sort of standard approach to sorting of data that presumably has been looked at and lots of person hours put into and should be pretty well optimized. Just like when we looked at mem copying, we saw it was actually a whole bunch of Intel assembly intrinsics, and it's pretty advanced in terms of how it's copying data. We don't need to write our own for loops for copying data generally. So the standard C library approach to sorting is called qsort, which I don't know if there was historical reasons it's called that, but if you look at the documentation, it's not guaranteed to be quicksort. But then you'll look at other references that strongly imply that it's implemented via quicksort. It's not guaranteed to be quicksort, but it's called qsort, and I think if you're mistaken for thinking of it as quicksort, I think you're not in terrible shape. It's an interesting function to use because it's actually more flexible than the code that we just wrote for merge sort and for bubble sort. It is a single function call that you just call qsort, and it's written in that standard library syntax, and we'll try to demystify that syntax in just a minute here. But it's actually a little interesting because you are calling this function qsort, and you're passing it the data you want to sort. So that part we can handle. But you're also actually having to provide a function that is determining what the less than operator means for your sorting purposes. And that's a little bit closer to kind of polymorphic and polymorphism in computing, in like that C++ and other higher level languages provide. In C, though, this is a little interesting, and this will be our first instance of using a so-called function pointer. That's what this last input is here to our qsort. So we can kind of figure this out, right? First input, that's the block of data you'd like to sort. How many data elements you'd like to sort, and how big is each data element? Very similar to our memory allocation class of functions. It's this third input this fourth input that's a little bit new to us. That is a pointer to a function that itself has a name and takes as input 2 pointers for the individual elements it would like you to compare. So qsort is, I still think, the right interview question answer of, how would I sort something, whether it's qsort. I've used the standard library for sorting because I'm not an algorithms person. It's not a good use of my time as an entry-level engineer to re-implement sorting algorithms. But getting this to work itself is not trivial. So let's explore qsort, and let's also just measure the performance of it to see how it does to our merge sort, which is reasonably efficient in terms of how we implemented it here. I have an example class exercise, which is sort an array of floats based on how close each float is to the nearest integer. Let's not do exactly, we could do that. First off, let's recognize that based on this flexible definition of how you call qsort, you can sort based on any criteria you can write up in code. Sort based on how close the number is to 47. We could do that. I mean, that's anything you can write in code and return a value is going to allow you to sort it using this mechanism. But for now, let's do the more boring sort of just ascending order of integers, and the code will be really similar as we decide to change our sorting criteria here. So this is example qsort, which is pretty empty. I'm actually going to go ahead and copy all of merge sort into qsort. This is still fine. Now we want to have like a q option as one of the inputs to the function. So we can do bubble sort, we can do merge sort, we can do q sort, else, and let's just make sure that option is there. Else if argv of 2, 0 equals q. And for now, we'll say doing q sort, although we don't have that implemented yet. Let's just make sure that all this stuff still compiles. Yeah, doing q sort. Well, it's not actually doing anything yet, but we have the hooks there. And I have the documentation open for q sort, and I just recognize that the syntax for it, for the comparison function, is a little bit out there. So let me just, as we do this, let me copy paste kind of the documentation for that part. And specifically for that third input, which should be listed here somewhere, comp, which is that input, comparison function, blah, 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 blah. I'm going to copy this whole block in because that's what we have to implement here. Okay, so qsort is what we have to call, and so our actual sort is a function that we ourselves are not writing. We're just calling qsort. And I think for these first three inputs, we can figure it out for our use case here. And then this comp, this last input here is a function that we're going to be passing to it. We're going to be passing actually the name of a function that we ourselves are going to have to write. Comp is going to be a comparison function which returns a negative integer value if the first argument is less than a second, a positive integer value if the first argument is greater than the second, and 0 if the arguments are equivalent. Qsort is going to call this function potentially many, many times to do the determination whether it needs to either swap or whether it needs to merge in a particular order. We actually, unless we look at the source code for our implementation, don't know exactly how many times it's going to use it. We could certainly have a printf inside the function if we want to debug how often it gets called, but for now, just being able to use it is probably sufficient. The signature of the comparison function should be equivalent to the following: int comp with one pointer input and another pointer input. The function must not modify the objects passed to it and must return consistent results when called for the same objects, regardless of their positions in the array. I'm a little curious why that's the case, but for now, I think it's sufficient to say we need to have this function in our code. We don't have to call it comp, my comparison function. That's a bit wordy, but that's fine. And this function, let me go back to this part here, and I'll move this thing up, this whole thing up here. Must return a negative integer if the first argument is less than the second, and a positive integer if the first argument is greater than the second. Well, we don't know what we're doing yet. Let's always return 1. So no matter what, we call my comparison function and it returns back out 1. That's going to do something. I'm not entirely sure what it's going to do. Let's have code that's going to print out our arrays again here. So that was already there. Let's add it back. And now when we're actually doing qsort, now we're actually going to be calling not my comparison function, but now you're going to call qsort, in which my comparison function is going to be an additional input to that call to qsort. Qsort's first input is a pointer to the array to be sorted. So what should we pass to it? For that first argument. Just array. Second input is the number of things we're sorting. What should that be? How many things are we sorting? Did someone say something? I couldn't hear. What was it? N, that's the right answer. We're sorting n things, right? That's our parameter to this code. How big is each item we're sorting? In terms of bytes is what it's asking. Yeah. Each thing we're sorting is an int. And finally, that last argument is the name of the function that is going to allow us to do the local comparisons for swapping and however it gets implemented. That's my comparison. I gotta make sure I spell it right. My comparison function. That is new. We have not done that all semester long, right? Which is pass the name of a function as an input, basically a function pointer to another function here. If I decide I have 5 different ways I want to sort the data, I just have to implement 5 different my comparison functions, and we can just call this qsort 5 different times with only that last input being different. Now, again, as we get our result here, we've not implemented, this is really auto-formatted off, actually wonky here. We have not actually implemented anything useful here. We're always returning 1, which says the first, it's going to give us something weird. Let's see what happens when we try it. Main, let's do 10 elements, and let's do bubble sort to make sure that works. That looks sorted, 10, and q. And it did something with the array. I don't know how well you can see all those little tiny numbers up on the screen there. It did something with the array, but it made a hash of it. It didn't actually sort the array. Because our comparison function isn't any good, right? It's just arbitrarily returning that the second, the first value is always greater than the second value, no matter how many times you compare it. That's not going to lead to any sorting value. But we can actually implement this here. If we want to then sort in order, the first thing you normally need to then do is say, okay, I have a pointer to the first element that's just called A, a pointer to the second element that's called B. I would just then create a local copy of those values. We'll call that int A, and it's just following A's pointer. I think to make our compiler happy, this is provided as like an untyped pointer here. We'd want to actually cast that pointer. So A is being passed in without any type information. We are now casting it to an int star. So instead of being just an arbitrary pointer, it's a pointer to an integer. And then we're following that pointer here, grabbing a value of A. That's the first value we're interested in. We would want to do the same thing for B. Now, I feel like I always get this backwards. Returns a negative integer if the first argument is less than the second. A positive integer, so it doesn't have to be -1 or 1, just something negative or 0 or positive. Instead of return 1 then, what can we return from this function? We want to return positive value if the first argument is greater than the second, and a negative value if the first one is less than the second, and 0 if they're equal to each other. What can we return then to give us that same result? Just subtract them. If we want to make a temp for int result equals int A minus int B, and return result. Let's run our sorting 10 values with bubble sort, sorting 10 values with quick sort, and it does correctly sort the values. Out of curiosity, if we ever want to figure out how many times does quick sort get called, you can always do that. Inside my comparison, with these input arguments, you could always do that just to debug. How many times is this getting called when we do our sort? A decent amount of times. Probably someone a little bit more clever than me could then take that information and figure out which algorithm it's using based on which comparisons are happening. It's hard. At first blush, it's hard for me to say exactly. It's first comparing 5 to 5, then it's comparing 1 to 9, then 3 to 1. I don't know. It could be some merge sort. I can't quite tell just by looking at it, to be frank. But we know it is doing a lot of those pairwise comparisons and presumably swapping on the result. It is, in fact, sorting the result that we have here. Now, let's get rid of the printing of the actual array here so that the runtime can be measured. And let's do some runtime comparison. Let's do 100,000. Let's do 10,000 just to get started. Oh, I should have commented out more. Let's try that again. Main 10,000 B, main 10,000 M, and main 10,000. Any guesses? You think quick Q sort's faster than our nice merge sort implementation? What do you think? Who thinks merge sort's faster? Because that's our code. We wrote that. We should be very proud of our code. Only you and me. Who thinks Q sort's faster? Okay. I don't know. I have not run this. I feel like Q sort has to support like really arbitrary data, and then it's calling this function each time. But it might be really well optimized, and it is very slightly faster than our merge sort. Let's crank it up a little bit. Let's not do bubble sort anymore for these sizes. So let's do million entry merge sort, million entry quick sort. Ah, interesting. Now merge sort does look to be a little faster in that case. Now 10 million, which will take us a little bit of time, but not too bad here. Right, this is measuring time, so smaller is better, right, in terms of the runtime of it. Take that standard C library. We have a faster implementation than yours, but which one is more likely to be correct and actually work, right? Also, so that's one reason to still be using this. Another reason to be using this potentially is just the flexibility it gives you. Where did my comparison function go here? If I wanted to sort this in descending order, literally that's the only change. The code does not have to change anymore, because then it returns the exact opposite result. If I wanted to return, what did it say on the slide here? That floats based on how close it is to each integer. Well, that one we can't do here, but sort based on how close each number is to 50. How would we do that? And we'd only want to run this for a small amount. So we'll run this and actually print out the result for sorting of size 50. How would we, or closest to 50? How close each number is 50? How would you calculate the distance a number is from 50? What would you do? Yeah, we can call that like distance A equals that, and it's either A minus 50 or 50, it doesn't matter, 50 minus int A. And we want the closer one to be the result we're interested in, which would be, we could still subtract them. Well, actually, we could still subtract them, right? So instead of doing result is int A minus int B, we could just do distance A minus distance B. Now, you can still do this in your bubble sort. You just have a custom comparison function. Here, though, it completely separates the actual comparison you're interested from the data you're generating, as well as from the actual structure of running the code here. Let's do main with 100. With bubble sort, of course, it's still going to sort it in ascending order. Now we do it with our Q sort implementation. And that looks about right. It's kind of hard to tell, but all the first few numbers are 50. Those are the ones with the closest distance. So maybe that's in descending order. I didn't really say. Either one is fine. I didn't specify, should 50 be the first element or the last element. Assuming we want it to be the last element, we get something like that, where there's a bunch of 50s at the end, and our really big and our really small numbers should be at the very beginning of our array here. Questions about QSort? Syntactically, what is new/interesting is this function pointer. So the fourth input here is saying, provide the function that's going to call that function for you, presumably using some quicksort or comparable type of implementation. It is based on whatever is in your standard C library implementation for that particular system. So the performance might vary. This printf of how many times it's calling printf inside comparison function may vary depending on the underlying implementation. But what it gives you then is basically just a ton of flexibility in terms of how you want to do those comparisons, and you can sort it however you'd potentially like to sort it. Questions about that? I was thinking we could just try to sort the dictionary instead. Do you remember words alpha that caused us all this pain for the monkeys typing example? These are in alphabetical order. What if we wanted to sort the actual dictionary, not in alphabetical order, but in length from longest words to shortest words, or it doesn't matter, or shortest words to longest words? That should be a very quick change as well. Qsort allows us to do that without too much structure in our code. Do you want to give it a try, or should we just give up for today? Show of hands, give it a try. Show of hands, give up for today. It was a tie. Let's do it. These are our last 2 sessions together. I'm going to miss you. I know you're going to miss me. Let's make the most of our very limited time we have together. This is an interesting problem in the sense that it does kind of combine basically everything we've learned all semester. Let's start this today. Please come back on Friday. Let's finish this on Friday. I think the challenge is it's an abstract problem of, sort the dictionary by length. And certainly even, 6 or 7 weeks ago, I think you'd look at that and say, I have no idea what that means. I have no idea where to begin. But I think combining basically all we've done all semester, we should be able to do this. First off, you would need to have a dictionary. So that's kind of has to be an input to the problem. We do have that file. It's words-alpha.txt. And I've even done that kind of very starter code for us, where we have to load the dictionary file and store the result somewhere. How would we do that? How would we store the result of all the words in a dictionary? What kind of data structure or variable are we going to need to be able to do that? We're going to need to have an array. How big does that array need to be? As long as, arguably, another way to answer that would be, okay, we could always look at the file and figure out how big the file is. But otherwise, for an arbitrary dictionary file, we don't know. We don't know how big it's going to be. So we need to have, what's that called? Dynamically allocated memory, maybe in 2 dimensions, right? We have a number of words in the dictionary. We don't know how many. And we have the size of each word in the dictionary, and we don't know how big that needs to be. So that, to me at least, would represent or indicate that we need kind of a 2-dimensional dynamic memory structure, something that we haven't had to do for any of your lab assignments, but we've kind of looked at the syntax for it before. If we need a 2-dimensional structure here, we'll call it the 2D array of words, where the one dimension is the number of words, and the other dimension is the size of each word. We'd want to have, that's our use case for that pointer to a pointer here, right? Kind of like how we would potentially declare an image. Here it's a little bit trickier because each word could be of a different size here. And we can just start it off, probably replit initializes it for us here. We have our in file. I think it's fair game to look at the file and know what's inside the file. I mean, it's not, and we could start with short list if we want to, as opposed to doing the whole dictionary. It's just a word, it's just text. 1 word per line is the format we're going to do here. What kind of function call would be appropriate for that, for reading that file? Any thoughts? We want to read from the file. So load the dictionary, store in the results. So we have to, read the dictionary and store into words. Okay. What function allows us to read an entry from that file? There's 2 we've used all semester. Either one would work. fscanf would absolutely work. The data is very regular. It's just a string on each line. fscanf takes the file first as input. The format string for what we're wanting to read, and then the variable we want to put the thing into. There's a little bit of a chicken and egg here in that we haven't defined the variable yet, so we may want to have enough space for a single word, something like that, where we define, okay, our largest possible word. So is this cheating? Is this fair? I don't know, but it's fine. For an individual word, won't be more than 64 bytes associated with the word. We want to read that in. And at that point, I say, let's test. Did we actually get the word we thought we wanted? Oh, because it is reading this file. Let's do short list instead, just because it's going to be a little bit more scalable for testing. Then we can always change it up later. First word is 1. Okay, we've read from the file. We have our first word here. We can use fscanf a number of ways. One way we can do it is check if we've reached end of file. But before we've done that, we want to now put that word into the larger words. How would we go about doing that? We have this It's nothing yet. It's not an array yet. We have this pointer to a pointer called words, and we need to make it of a certain size. How big does that array need to be once we've read in the first entry into that word, into that array word? Somewhere we certainly have to keep track of the number of words. So it's 0, let's assume. We've read a word. That means we do have at least one word. We can do that much. We read a word. We have one word. What does our words pointer need to be then? How big should it be, at least? We need to dynamically allocate it. I agree with that. And malloc is going to be a little tricky in that we don't know how big to allocate it, but realloc should be okay, because we're just going to take the pointer that we already had and make it one bigger, or make it num words bigger. So that syntax should still work for us. So words is this pointer. It is not just a char star, it's a char star star. We would call realloc, which takes the pointer itself to begin with, and the number of words we want to allocate is going to be that big. That would then now, once we've done that, now words of 0 is going to be a valid entry into that array. Words of 1 would still be invalid, but words of 0 would be valid. That's not quite it, though. That allocates, you could think of that as a row in our two-dimensional array. We also need to then allocate the space for the actual word itself. That wouldn't just be words now. That would be the new entry we've just created in words. 0 would be fine only in the first case. It'd be words of num words minus 1. That is now, if words is a char star star, words of a certain offset is a char star. It's a pointer now to a string that we still have to allocate. Here, malloc is probably still okay, because we could also use realloc, but malloc is okay because we're only doing this once. We have a new entry in the dictionary. We have allocated that space for it. We now need to allocate the space for the word that's going to go in that location in the dictionary. So that would just be malloc. How many bytes do we need to allocate for that word? You could do max word length. That would work. It would just be kind of a waste of memory. How big does it need to be? Now we got our string length of the word we just grabbed. And we did this, and we kind of trial and errored this. I think we want one more byte. Right? That was a quiz question that we were all unhappy with after it ended, right? Because string length tells you like how many valid characters there are. Now that we're dynamically allocating this word in the dictionary, we need one more byte for the null pointer that's going to get copied over into the end. That should be correct. And then we actually do need to do that string copy. String copy, destination is first. It's words of num words minus 1, and then word. And just to confirm we're not crazy with this initial test, first word is this, and now let's not print out words, let's print out words of 0. Did we actually get something in our dictionary, or did we segfault? Okay. And actually we're almost, well, I know we have to go, but we are almost done, right? I like this approach. We've done it both ways all semester, right? Sometimes we've started with like our structured loop, and then tried to figure out what would go inside the loop. Here, because I think what's inside loop was reasonably complicated, we did kind of the exact opposite. This would be the body of a loop. And now we gotta wrap a loop structure around it. But it's really not that bad. Let's just do it very quickly here. fscanf, I always get this confused. fscanf returns the number of things matched. While we are still getting something valid out of fscanf, do that. That's it. See if it crashes. Nope, no crash. And then now we can do a for loop if we want to just print them out. I should have kept that, but word D is this, I, and words of I. Let's leave this at here for today. We haven't actually sorted the dictionary at all. Just to make sure we're not going crazy, let's just do the really long one again, just to make sure. It's going to print out a lot, but it shouldn't give us a memory error at the very least. and it looks like it's going pretty strong. So we will leave things at here for today. We haven't sorted the dictionary yet. The problem is already set up for us. We have one more line of code to write to sort this entire dictionary, and then some more lines depending on how we want to sort the dictionary, but it's completely separated. We can do those in two separate stages. Leave things here for today. We'll finish this example on Friday and hopefully do one more example in our last time together.